So in this lesson, we're going to learn about some first-order differential equation applications. Now, we can't get into too many. We're just talking about first order here, but we can at least talk about some applications I'm sure that you've seen before in other classes, not realizing necessarily they were differential equation applications. So in this case, let's look at some models here. And so usually when you mathematically model any situation, it tends to take the form of a differential equation. It's an equation that has some unknown functions and some derivatives of those functions. It's not too surprising that this would happen in a real world situation. I mean, think about it. Anytime you notice that things are changing or changes are occurring, and we want to predict maybe the future behavior based on those current values changing, that's exactly what calculus is all about, and therefore differential equations. So most mathematical models of real-world applications are differential equations. The most common application that you would see at this point in a course like this, when we've just got done talking about linear equations not that long ago, is population growth or decay. And so this is a very simple linear equation that would describe this. We usually talk about this first when the population grows at a rate that's proportional to the size of the population. That's a pretty key here to this first growth model that we look at. And it's just basically saying that, based off of whatever size of the population we have, the change in the population or the rate in which it's going to grow, or we can even say decay, has to do with that size itself. And so, it's a pretty reasonable assumption under some circumstances. It's reasonable when we talk about, say, bacteria growth or animals, under ideal conditions like, say, rabbits or rats or something like that multiplying. Now, it's under ideal conditions. You have an unlimited environment, adequate nutrition, absence of predators, immunity from disease. It's not the perfect scenario necessarily, but it's really looking at this ideal conditions, which isn't 100% accurate all the time. So anyway, if we look at a couple of variables that we're going to work with in this model, we're going to talk about t. Everything's going to be dependent on t. So t is going to be your independent variable. P is going to represent the number of individuals in our population. That'll be our dependent variable. So instead of x and y's, we'll use t's and p's here. So the rate of growth we'll also talk about being the derivative of p with respect to t. So if we use that assumption that our rate of growth of a population is proportional to the population size, then this is the equation we would be talking about, where the change or the rate of growth, if it's proportional to population size, it's a multiple of the population size. And k is that multiple, which we'll call the constant, proportionality constant, k. So it's a really simple equation, but it is a first order differential equation. P being the dependent variable, which we would have to solve for, and t being the independent variable. If you notice, this equation is both separable and linear. So like we said, this differential equation contains the unknown p, which we would solve for. So we basically have to figure out what p of t equals, would be the solution to the differential equation, and it also deals with the derivative of p. So we can use this equation for a lot of things. We can use it for radioactive decay, which we'll do an example of that. We can talk about it in chemical reactions and looking at the remaining substance that's left over during a chemical reaction. And we could also talk about it in terms of population growth, bacterial growth, viral growth, whatever. Okay? So this proportionality constant is something that we're going to need to solve for when we're setting this equation up and trying to find the solution to the equation. And we can do that just by looking at some subsequent measurements of p at time t. So essentially some initial conditions is really what we're going to need, and this is where the initial value problems start to play a role. So if we start to think about solutions to this equation, right? Basically the idea of solutions to this equation is we're trying to figure out what function has a derivative that's equal to some multiple of the original function. Okay? So we have a function and its derivative is the same as the original, just a multiple of the original. Well, functions that do that, exponential functions do that. Okay? Exponential functions have that idea where if you take the derivative of this, say, exponential function, you rewrite the exponential and multiply by the derivative of the exponent. So you get c k e to the kt, pull the k all the way out, you have the original function, which means you have a multiple of the original function. And this is why you hear a lot of exponential growth. When you hear about populations growing, you hear about them growing exponentially. The reason being is most population growth can be talked about in this simple equation. There's other population growth equations. There's something called the logistic equation. But if you're just talking about simple growth, this is the equation that describes that, and the solution to this simple equation is an exponential function. So here's a fairly simple example. So we have a bacteria growth problem here. So a culture initially has T sub 0 number of bacteria, okay? So it's the initial amount. So that means when time is 0, P of 0 will equal P sub 0, this initial amount. I could have given you a specific number amount, like 10,000 bacteria is what you're starting off with. But I just label it as P sub 0 here because it could be any initial amount. So we could use this for other problems as well. And then at time of 1, and when t equals 1 hour, the number of bacteria measured is 3/2 the initial amount. So what that's telling me is that when p of 1, when time is 1, we plug 1 into this p function, we're going to get 3/2. So 1.5 times the initial amount after 1 hour. All right. So if the growth rate is proportional to the number of bacteria present, so we have that proportionality, which means we're going to deal with that model we just talked about, then determine the time necessary for the bacteria to triple. Well, that's a separate question. So this part here, we can't answer till we find the function that describes the rate of growth. Okay? So this equation, dp dt equals kp, you can say p of t or whatever, however you want to write it. This equation is the differential equation that models this situation because of the proportionality of growth. We need to find what function will satisfy this equation given these conditions. And then once we find the function that describes the growth that's happening here, we can then determine the time it will take for the number of bacteria to triple. Okay? So let's solve this equation first. Again, it's going to be an exponential function, but let's see that happening in our solving process through differential equations. So this is a linear equation. I could rewrite this as dp dt minus kp of t equals 0. P is my dependent, T is my independent. You see this is my standard linear where we're equal to 0 on this side. That's my F. And here is your P, not the same P, but this is the P that we would use for our integrating factor. So we have our integrating factor mu of T to be e to the integral of negative k dt, which would give us e to the negative kt. Remember, we skip a couple steps in our linear process. We get to the point where we would have the integrating factor times the dependent variable. So that would be e to the negative kt times P of t equals the integral of this function, which is 0, times the integrating factor, so that is the integral of 0. So what do we get here? We get e to the negative kt times P of t equals c. So then divide this over or multiply this over with a positive exponent, and you find that P of t equals c e to the kt. Again, we knew that was going to happen. We saw that a second ago when we just kind of looked at what could possibly solve this differential equation. But now you see it happening through our methods of solving linear differential equations, right? Okay, so we have a couple of things here. This is the function, but there's a lot of constants happening here. We have c, we have k. All right, we want to find the specific function that solves this differential equation and satisfies these conditions. So we're going to have to look for these variables. So let's look at the first condition. We know that P of 0 equals P sub 0. So when I plug 0 in for t into this P of t, I should get P of 0. Well, if I do that, I'm going to get c e to the k times 0. Okay? That's plugging 0 into here. Well, e to the 0, this here is 0, so e to 0 is 1. So this says P of 0 equals c. So now we have c. All right, so now what we have is not just P of t equals this, but P of t equals P sub 0 e to the kt. All right, now we want to figure out what our constant is, our proportionality constant, and then we'll have the entire function. So once we have that proportionality constant, we'll use the next condition, that P of 1 equals 3/2 P sub 0. So when I plug 1 into this, which would be P sub 0 e to the k times 1, I'm going to need to see if I can find k. Well, I can find k because here these two P sub 0s will cancel. I divide it out. I get 3/2 equals e to the k. Then I can get rid of the e by taking the log of both sides. So log of 3/2, log of 3/2 equals k. So using that as my k value, when we said c would be my initial value, P sub 0, whatever the initial amount of bacteria is, then we can write our P of t. Just to make this a little easier to write, I'm going to say the log of 3/2, put in my calculator, it's roughly 0.4055. So then my P of t function that will describe the growth that we just talked about would be P sub 0 e to the 0.4055 t. So that's the proportionality constant for this problem based off of a little bit of growth that we saw from the initial amount to the 1 hour mark. All right, so now what we want to know is how long is it going to take for the amount of bacteria to triple? So we have an initial amount of P sub 0. If it were to triple, it would be 3 times the initial amount. So what we want to know is, when will this, okay, be equal to 3 times the initial amount, which would be triple the initial amount? Well, if we could solve this equation here for t, we could figure out how long it will take for that to happen. So if we solve this, it's pretty simple. Divide the P sub 0 out. Take the log of both sides. So log of e to the 0.4055 t equals 3. These log of 3. These cancel. 0.4055 t equals log of 3. Divide by this, 0.4055, and we get t to be the log of 3 over 0.4055, okay? Which is roughly 2.71, and our time was measured in hours, so hours. So roughly 2.71 hours for the amount of bacteria to triple. If I want to know how long it's going to take for it to, be 10 times the initial amount, then all I do is I change this number right here, and that'll change this value here, and I could describe this. I mean, this is the type of thing you could see happening, in a lot of population growth problems. And now why would this be important? Because when we have this function here that describes the growth rate, so P of t equals the initial amount e to the 0.4055 t, once we have that function, we could then use that to predict a lot of future events in this bacterial growth. When's it going to triple? When's it going to quadruple? When's it going to be 1,000,000 times what it was originally? This could be useful. Think about it in terms of viral transmission. We want to know when there's going to be, 20,000 cases of a particular virus. And so you could look at the modeling of what that virus is doing in terms of, how fast is it replicating in the beginning, and try and use that to predict how fast it's going to replicate later down the road, and whether or not that's going to cause an issue. And so, this simple equation, which has a fairly simple solution, is used for a lot of things. Here is another example, but it's looking at it in the opposite manner, in which case we're talking about decay. I mean, if we have an exponential function, growth versus decay model, it really just depends on whether or not the exponent itself is positive or negative. When you think about an exponential function, y equals e to the t. If you think of t to be positive, you have this type of growth model. And if we look at an exponential function where t is negative, so we look at it that way, negative exponent, we have a decay model. And so we saw our proportionality constant created a positive exponent in our previous example. This one, since it's a decay process situation, we're going to have a negative constant as our proportionality constant in this model. But we're still working with the proportionality of in our rate of change. So let's take a look at this problem. A breeder reactor converts the relatively stable uranium-238 into the isotope plutonium-239. After 15 years, it is determined that 0.0043% of the initial amount, say A sub 0 is the initial amount, of plutonium has disintegrated. Find the half-life of the isotope if the rate of disintegration is proportional to the amount remaining at time t. Well, again, that second part, find the half-life, that's a separate question. We need to find the function that models this type of decay, okay? And then once we find the function that models that type of decay, then we can answer questions about the half-life. In previous classes, you may have seen something like this. In another class, maybe in chemistry, something like that. And they would have asked you about the half-life of an isotope, but they would have given you the function already that describes the decay. In this case, we can find the function that describes the decay because we can solve the differential equation. So you've been dealing with these types of things for a long time in your other classes, biology, chemistry, physics, engineering, whatever, but you never really see where the functions are coming from. You just are given them. In this case, we are now solving for those functions based off of some information. So let's look at this. We have an initial amount. So let's use A as our dependent variable now. We have an initial amount of A sub 0. So at time of 0, we have A sub 0 amount. Okay? And after 15 years, okay, we know we have a certain amount left. Well, we know how much is disintegrated. If 0.0043% is gone, right, it's disintegrated, then what do we know? We know that 99.9% 0.9957% is left. Okay? So after 15 years, we have 0.999957 times the initial amount. Okay? All right. Well, we have this equation that, in this case, dA dt equals k times a of t. And we know the solution to this. I'm just changing the variables from p's to a's. So we know the solution to this is going to be a of t equals c to the times e to the kt. Okay? We already know that's the solution to this equation. I don't need to solve it again. So what we need to do, though, is we need to use this information to help us find the exact function that will describe the disintegration of this plutonium. Well, the initial amount is the same as in previous, so we also know that a sub t, or a of t, equals a sub 0 e to the kt. I think we could jump straight to there by solving for that c the same exact way. Here's the big thing. Now we jump to 15 years, this is it. So if we jump to 15 years, we know that at 15, so e to the k times 15, at 15 years, this should be equal to 0.999957 times the initial amount. Okay? And so if we cancel those out by dividing it, and then we get rid of the e by taking the log, we have k times 15 equals the log of 0.999957. Divide by 15, you got your proportionality constant. So log of 0.999957 over 15 will get you your constant. So roughly that constant would be, it's right over here, negative 0.00000, so 5 zeros, 2867. Okay? So my function that's going to describe the decay of this uranium into plutonium would be a sub 0, whatever the initial amount is. So if I had, I don't know, 10 grams of the plutonium, something like that, that would be a sub 0, e to the negative 0.000002867 t. And notice we have a negative exponent because of the decay. So that's the function that will model the decay of plutonium. So now what we want to know is find the half-life. Well, half-life means half of the initial amount is left. We just figured out after 15 years, we still have a lot of the initial amount left. We want to know when half of it will be left. That's what half-life means. So when will this be equal to 1/2 the initial amount? So if we solve that equation for t, we could find what we're looking for. So we have a sub 0 e to the negative 0.0000287 equals, or t equals 1/2 a sub 0. Okay, the a sub zeros will cancel each other out by dividing. I get rid of the e by taking the log, so then negative 0.0000287 t equals the log of 1/2. Okay, that gets rid of that e by taking the log, divide by this, and you find that t is the log of 1/2 over negative 0.0000287. And so this will be roughly 241,767 years. That's a lot, right? It's going to take a long time to have half of this left over. But nonetheless, that's it. But because we were able to find the function that models the decay of this plutonium, which was this A sub 0 e to the negative 0.000002867 t, we could then predict how long the half-life would be. And so that's the benefit of being able to find the solution to differential equations based off of some conditions that we have. So there's our growth model / decay model application. Our next application has to do with electrical circuits. So if we consider a simple circuit that we see below, where we have an electromotive force, this is usually a battery or a generator that produces a particular voltage, E sub t, that's measured in volts. Then we have a current that's running through this circuit, I of t, that's measured in amps at time t, and that'll be the dependent variable that we're going to actually solve for here in this circuit. The circuit also contains a resistor with a resistance of R measured in ohms, and then we also have an inductor with an inductance of L henries. Okay, and so this is your typical circuit you would see. Very simple circuit if you ever dealt with circuits. So we have Ohm's law. Ohm's law gives the drop in voltage due to the resistor as R times I. Okay, so that resistance times the current. The voltage drop due to the inductor is L times the change in I over time. This derivative of I with respect to t here is going to be the change in the current over time. So L, which is the inductance, times that will give us the drop in voltage due to the inductor. So that's some of Ohm's law. Then we also have Kirchhoff's law. Okay, says that the sum of the voltage drop is equal to the supplied voltage. Okay, E of t. So that gives us this basic equation that describes, this voltage and the current in the simple circuit. So if you notice, this is a differential equation. It's an equation that has the derivative of I with respect to t as well as I. Again, I is going to be our function that we're solving for in this. So we're going to solve for the current function in this equation. And this is a first-order linear differential equation for I. Again, the solution will be I, the current, at time t. So, since this is a differential equation, this falls right into what we're doing. This is a basic application of differential equations by talking about a simple circuit. So here's an example. So suppose we have a simple circuit. The resistance is 12 ohms. The inductance is 4 henries. Okay? If the battery gives a constant voltage, okay, of 60 volts, so this is powered by a battery, it's giving a constant voltage of 60 volts, and the switch is closed when t equals 0, so the current starts with essentially I of 0 equals 0, find I of t. Okay. Then after we have I of t, the function that'll satisfy the differential equation and give us the current, we want to find the current after 1 second, and then we want to find the limiting value of the current. Okay, so there's really 3 questions here, but first we need to find the function that would describe the current flowing through this circuit. So we have this differential equation, L times di dt plus R times I equals E of t. Now, this problem told us that L is going to be 4 henries, that R is 12 ohms, that's ohms, and the voltage, E of t, is a constant voltage of 60 volts. So if we plug all that in, we're going to get 4 di dt plus R, which is 12, times I, equals 60. And so you see this is a very simple linear differential equation. So we'll put in standard form, divide everything through by 4, so we get di dt plus 3I equals 15. Here's your P of t. Here's your F. So we find our u of t, our integrating factor, e to the integral of 3 dt, which gives us e to the 3t. So we skip down to the point where we get I times e to the 3t equals the integral of 15 e to the 3t dt. Okay, this times this. So it's a pretty simple integral. So I e to the 3t equals, if you integrate e to the 3t, you have to divide by 3 when you integrate, so this is going to turn into 5e to the 3t plus c. So you solve for I, so I of t equals divide by e to the 3t, you're going to get 5 plus c e to the negative 3t. Okay? So there is your I of t, but we have the c that we need to solve for. That's where the I of 0 equals 0 comes into play. It's the initial value. So if we plug that initial value in here, t equals 0, I of t equals 0. So we're going to get 0 equals 5 plus c e to the 0. So you see here easily that c equals negative 5. So my I of t current function for this particular situation is going to be 5 minus 5e to the negative 3t. Okay, so there is your current function. That was the first part of this question. Now the second part of this question says find the current after 1 second. So basically find I of 1. All right, well that's easy. Just plug 1 in for t now that we have the current function. So 5 minus 5e to the negative 3, okay, which if you want to plug that in your calculator, that's roughly 4.75 amps. Okay, so at 1 second we have 4.75 amps running through this circuit. That's the voltage, okay, or sorry, that's the current, I should say. All right, so once we have that, the last part says, then find the limiting value of the current. Now this is important because as t moves on, as time keeps going and going and going, what happens to this current? Does the current keep increasing more and more and more and more, in which case that's a problem. You know, if you have an electrical circuit, you don't want the current to increase and increase and increase. That could burn out the circuit. So what's the limiting value here? As time moves on, how does this current move through this circuit? So if we looked at the limit as t goes to infinity of this I of t, so 5 minus 5e to the negative 3t, okay, what happens? Well, if you look at t going to infinity here, this is a constant, so the limit of a constant is that constant. This thing right here, as t goes to infinity, since it's got a negative exponent, you know, this thing's going to go to 0, okay? Because really this is 1 over e to the 3t, and so the denominator is going to get very, very big, making the whole fraction go to 0. So essentially the limiting value here is 5. So the current's going to top out at 5 amps. Okay? And so that's important to know that the current flowing through this circuit is going to top out at 5 amps. And then you can, you know, take your current or your pieces that make up this simple circuit, and you can keep them at a certain point. You can use the materials that you need that can handle the 5 amps. Okay? So it was 3 questions in one, but really the big question was find the current function. And we did that by solving this differential equation. So another example of simple differential equations. Now what if we change things up a little bit? What if we, instead of having a constant voltage flowing through this of 60 volts, what if we have a variable voltage? So instead of a battery, we use a generator. And a generator will tend to not give out the same voltage all the time. It'll vary up and down and up and down and up and down as that generator, you know, runs. So typically you'll see the voltage in a trigonometric function, so that it goes up and then down and then up and then down and up and then down. So it's varying up and down like that. So this wave pattern. So let's say we have that. Well, everything's the same in this, so we'll still have 4 di dt. We still have 4 henries as our inductance. We still have 12 ohms as our resistance. So 12I equals E of t now, though, is this 60 sine of 30t. Well, it's still a linear differential equation. We're going to get a different I of t, though, to solve this. So what we need to do is put in standard form, divide by 4. So di dt plus 3I equals 15 sine 30t. We're still going to have the same mu, so the mu of t is still going to be the exact same, e to the 3t. And so we're going to get to the point where we have I times e to the 3t equals the integral of 15 sine 30t times e to the 3t dt. Okay, and so what we're going to need to do is we're going to need to solve that integral. It's a little bit harder integral than the previous integral. And so we're going to need integration by parts to do that. And so if we use integration by parts to do this, this is going to be one of those integration by parts that's going to be repeated over and over, and you're going to loop back to the original integral. And so what's going to end up happening here is that this integral is going to turn into 50 over 101 e to the 3t times sine 30t minus 10 cosine 30t plus c. Okay, so that's how that's going to work out after you do integration by parts. We'll divide by the e to the 3t because we still have that over here. And so what we end up with is I of t equals 5 over 101 times sine 30t minus 10 cosine 30t, that should be a 30, plus c e to the negative 3t. Okay? But, nonetheless, if you have a variable voltage versus a constant voltage, it's still a linear differential equation, and you could do it. And so, if we change that up, we could then look at, okay, what would be the current after 1 second? We can then look at the limit of the current. We could do all the same things we did in the last question, and this will give us the current flowing through that circuit at any given point in time. But clearly, because this is a functional value for the voltage, the integral that we get here is going to be more difficult. So it's a basic integration by parts integral. In which case, you would let u equal, say, 15 sine 30t, and dv could be e to the 3t dt. And you would just move on from there. It's going to be one of those repetition integration by parts integrals, where your du and your v will give you another integral. This one's going to give you 1/3 e to the 3t, and this one's going to give you a cosine. So in this case, we're going to have 15 over 30 cosine 30t dt, and then this will be the next integral you do, which it looks a lot like the original integral, and then this will be your next u, this will be your next dv, and you keep going. Okay? A final application that we're going to look at is a mixture problem. Now, this is not the last type of application we could possibly do. I mean, we could keep going and going and going with applications, but I think, one more should be suffice to show you that there's a lot of applications, even just for first-order differential equations. So the typical mixing problem here involves a tank, a fixed capacity containing a thoroughly mixed solution of a substance, maybe salt, okay, and the solution of a given concentration enters the tank at a fixed rate
and there's a mixture that's thoroughly stirred, leaves at a fixed rate, which may differ from the amount that's entering, so that, it enter at a different rate than the amount leaving. So if Y of t denotes the amount of substance in the tank at any time t, and Y prime of t is the rate at which the substance is being added minus the rate at which it's being removed, we could say this is your basic equation that would describe what's happening here. dy dt, which is Y prime, okay, is equal to the rate in minus the rate out. This essentially would be your first order differential equation. We could say that it's a separable equation, okay, of what you're going to end up seeing. And since it's separable, we're definitely able to solve it. We can use the same type of reasoning to model other phenomena, say chemical reactions, discharge of pollutants into a lake, injection of drugs into a bloodstream. It's all basically the same mixture problem. Okay, and we would use the same general model to describe that the change in Y is the rate of change of the substance being added minus the rate in which it's being removed. Okay? So here's your example. The tank contains 20 kilograms of salt dissolved in 5,000 liters of water. Okay? The brine that contains 0.03 kilograms of salt per liter of water is entering the tank at a rate of 25 liters per minute. The solution is kept thoroughly mixed and drains from the tank at the same rate. Okay? How much salt will there be in the tank after half an hour? Well, we would have to find the function that measures how much salt will be left in the tank after a certain amount of time. Okay? And then once we do that, we could plug 1/2 an hour into that function and find out how much. But we need to find the function that describes the amount of salt left in the tank after a certain amount of time, so dependent on time. So this tank has 20 kilograms of salt in 5,000 liters of water. The brine is 0.03 kilograms of salt per liter. Okay? And the rate in which it's entering the tank, rate is always derivative, is 25 liters per minute. Okay? So if we look at the rate in, the rate in of the brine would be the amount times the rate, right? So the amount times the rate. In this case, it's 0.03, and this would be kilograms per liter, times the 25 liters per minute. And so if you notice, these liters will cancel. In the end, we're going to get 0.75 kilograms per minute. So that's your rate in. Okay? Then, if we look at it, we want the rate out. Okay? This keeps erasing. The rate out. We want to do the same thing. We want to do the amount. Okay? So we want the kilograms per liter, and we want the rate. Well, the rate is the same. Okay? Notice it says that the solution is kept thoroughly mixed and drains from the tank at the same rate. So this will still be 25 liters per minute. But we want to figure out the amount there. Well, what we have here is a function that's going to be changing. Okay? The amount in the tank and the rate out will change depend on the amount of solution in the tank initially. And then the amount that's in there after the brine is added. And so we know that it's a 5,000 liter tank. But the amount of salt is going to be changing, right? It starts at 20 kilograms, but it's going to be changing because we're adding a certain amount. So what we're going to do is we're going to describe the amount of salt per 5,000 liters as a function y of t, where y of t is the amount of salt after t minutes in the tank, okay? And so if we did this, what we're basically going to have is y of t over 200, okay, because 25 divided by 5,000 kilograms per minute, okay? Because again, the liters will cancel and be left with kilograms per minute. So if the change in salt concentration over time is equal to the rate in minus the rate out, okay, then my differential equation should be dy dt equals 0.75 kilograms per minute minus y of t over 200 kilograms per minute. And so what you need to notice is that this is actually going to be a separable equation. I can write this as one fraction. So dy dt equals, common denominator is 200. I end up with 150 minus y of t in the top. I can then separate, and I basically am going to get dy over 150 minus y of t equals dt over 200. So here's my separation of variables. Okay, y is the function over here, y with dy. I integrate both sides of this to solve the separable equation. What's going to happen here is I'm going to end up with a logarithm on the left-hand side. On the right-hand side, I'm just going to have, this is a constant, so this is just going to be 1 over 200t. Okay, I'll throw a plus c somewhere, I'll put plus c here. Again, over here, this will be a logarithm. I have a u and a du. I'm going to be off by a negative, so I'm going to get negative log of 150 minus y of t, however you want to write that. And then from there, I could finish solving this for y. Now remember, we also had the condition that initially we had 20 kilograms of salt in the tank. That was the original amount of salt we had in the tank. So essentially what we're saying is y of 0 equals 20. And that'll help us find the c value. So we could solve for y now and then find the c. We can solve for y, if we solve for c first and then solve for y to find our function. I mean, however you want to do this, we can. I think it's pretty easy to find c right now. So we're going to use this initial condition to find c before we simplify this equation. It really doesn't matter. So if y of 0 equals 20, what that tells us is that the y is 20 and the t is 0. So what we end up with is negative log of 150 minus 20 would be 130 equals t, which is 0 times 200 plus c, so we get c. So right away there's your c, pretty easy to find. So then what we're going to see is that our function equation would be minus log of 150 minus y equals 1 over 200 t minus log of 130. Okay. And what we can do is we can then try and solve for y. Pretty easy. We'll try and get rid of the logarithms. We get rid of the logarithms by using e, and then go from there. So we have minus log of 150 minus y equals t over 200 minus log of 130, e on both sides. So we'll bring this negative, I'll push this negative through to the other side, right, before I use e. So I'll go log 150 minus y equals log 130 minus t over 200. So by multiplying this log, this negates the other side. This is now negative, this is positive, so it just flips those around. Okay. Then e on both sides will give me 150 minus y equals e to the log 130 minus t over 200. But I could write that as e to the log 130 over, or times e to the negative t over 200. Okay. Now that'll allow these to cancel as well. So I end up with 150 minus y equals 130 e to the negative t over 200. Now I want to get rid of this absolute value. Now that's kind of the tricky part. So a couple of things, right? Our function y of t is going to be continuous, right? Because y of t represents the amount of solution in the tank at any point in time, and that's going to be a continuous function. We also know that y of 0 equals 20, okay? So essentially what that's telling us here is that if you look at this, you can tell that this is never going to be 0, and since this is a continuous function and we know that we get a positive value here, what it's basically telling us is that this thing in here is always positive. If that's the case, then that means we could just drop off the absolute values. So we end up with 150 minus y equals this 130 e to the negative t over 200, and therefore our y of t ends up being 150 minus 130 e to the negative t over 200. All right, so we got our function. You know, there's a little bit of work to get to the function at this point, but then once we have our function, how about we look at the amount of salt after a certain amount of time. Well, if you notice, all our measurements were based off of per minute. So it's at a half an hour, so we're going to go with 30 minutes. So if we find y of 30, that'll tell us how much salt we have in 30 minutes. So we plug 30 in for t here, and you're going to roughly get 38.1 kilograms of salt concentration in the tank. So that last part was just then using the function we found that was the solution to our differential equation to answer some piece. But really the point was that we had to find the solution function to that differential equation, and we did it through separable variables. So there's a couple of examples of applications of differential equations, specifically first order differential equations. Again, they're not the only examples, but they're some of the simpler examples we can go through, and you see that there are many applications, lots of uses of differential equations in real world time. And a lot of this you have seen before. You've done this type of problem in other classes. You just didn't do the differential equations component of it. You would start with the function that was the solution. This would have been given to you already, but now we can find those functions based off of some of the conditions that were given.